Hello everyone, I am Saeed Tisbaz-Niari from CEO Boulder. I recently received my PhD and I will start as an assistant professor of CS at University of Texas, El Paso this fall. Today I will present DPFuzz that aims to detect and explain differential performance bugs with focus on machine learning libraries. This is a joint work with Pavel Cherny from TUPN and Ashutosh Triverdi from CEO Boulder. Outlines of these talks are the problem, differential performance bugs, our approach that combine fuzzing and debugging, and finally, the evaluation of our approach with experiments. Let's start off with the problem. What are differential performance bugs? I want to take few examples to illustrate these type of bugs. Example one is SnapBuddy. SnapBuddy is a mock social network application developed as a part of DARPA stack program for research purposes. In this application, every user has a public profile with an image. For example, Ashutosh is a user in the application. He asked for his public profile and it took 1 unit for SnapBuddy to respond. Whereas Anya is another user in the system, she also asked for the public profile and it took longer for SnapBuddy, 5 units in this case, to retrieve her public profile. These differences between response times for the public profile of Ashutosh and Anya are somehow unexpected and susceptible for differential performance bugs. Example 2 is for ApacheFob, where a user reported that they had 2 very similar inputs, but for one, it took 7 times more to respond by ApacheFob than the other one. When we profile the ApacheFob, we are observing there is a constant time behavior and there is also another nonlinear behavior. So this is also susceptible for differential performance bugs. Finally, and most importantly for the purpose of this talk is for machine learning library, where a user of scikit-learn libraries reported that they observed significant performance degradation in applying regression trees with MAE criterion as compared to MSE criterion. And in this plot, you can see the performance time versus the size, where there are different modes in the response time. All of these challenges arise the question, how could we detect and understand differential performance bugs? They can lead to inconvenient services, waste hardware resources, and even cause security issues. It turns out that there are requirements. Requirement 1 is to generate diverse input, not just the worst case one. Existing performance fuzzers such as slow fuzz and pair fuzz focus on the worst case performance. They are looking for a single input that can cause huge degradation in the performance. Whereas differential performance bug may not necessarily manifest from the worst case performance. In the plot bottom, you can imagine that the differential performance bugs are manifested from mode 2 and mode 4. None of them are the worst case one. Therefore, we require to generate inputs to explore as many performance as possible. Requirement 2 is for debugging or profiling. Unlike worst case performance, where the user needs a single bad input to profile the system and find out what component contributes to that, in the case of differential performance debugging, the debugger needs to run at least 2 profilers at the same time for 2 inputs and compare the results to find out the root cause. In case if the debugger had multiple performance modes, they need to basically run multiple instances of profiler at the same time and compare the results. We cannot expect human analysis to do this manually. We need an automatic tool. All these challenges and requirements motivated us to develop a data-driven approach that combined fuzzing with debugging to address them. And this brings me to the second part of this talk, that is our approach. I showed the workflow of our approach DPFuzz. Our approach has two phases. The first phase is to generate interesting inputs, to manifest differential performance bugs. The second phase takes the inputs and further analyze them using features from the space of the input and program internals to localize and explain the root cause of differential performance issues. Let's focus on the phase one that adopts gray box evolutionary fuzzing to manifest differential performance bugs. So we have a simple representation of a program as a control flow graph. As we know, an input may visit a sequence of basic blocks, or you can imagine as a sequence of lines in the code. It may satisfy a condition such as condition C1 and took a loop few times until it reaches to the end part of the program. So we use a notion of performance as a cost, and it's represented as a number of lines executed. So this is similar to our performance fuzzers. But one important difference is in the model of the population. We consider a simple path as a representation for the population. For example, trace tau1 and tau4, they are from two different inputs and visit basic block 4 and 5 different times, as you can see, but they visited the same set of basic blocks, or you can imagine as a line executed. Thus, we put them in the same population, whereas the trace tau2 and tau3 are in different population. This is to be able to use this population to model performance functions. The second difference is for a group of population. And in this control flow graph, input satisfy condition C1 and input satisfy condition C3 are in different paths and different population, but they have the same class of complexity. They are in the same group of the population. So in this case, in this simple control flow graph, we may have three population, but we put population 1 and population 3 in the same group, and we use this information to focus on few groups of population with significantly different performance, as opposed to all possible population. Many of those may have similar performance characteristics. This concludes the fuzzing part. Let's move on the debugging part. So we take input from the fuzzing. We first do a clustering to basically detect different classes of performances. In this case, we obtain 3 clusters. The fact that there are multiple clusters lead us to the next step to explain them based on features from program input. So table 1 shows different features for different inputs such as tolerance, penalty, and solver, and we have labeled from clustering. One way to find a similarity and differences between the clustering is to use decision tree. In step 3, decision tree number 1 shows an explanation model based on the program input features. In particular, for example, it says that if the solver is STD and the tolerance is equal to 0, then we are in brown cluster. Depending on this explanation, we may find some aspects unexpected. For example, the differences between tolerance become 0 and bigger than 0. So we take the analysis further using instrumented version of the program, and we generate internal traces such as method calls, function calls, or like condition statement calls. And we build or form table 2 that for each input shows like how many times a function is called or whether a condition was true or not. And we have the label from the clustering for different inputs. Again, decision tree number 2 at step 5 explain the root cause of the problem. For example, it says that if the function f3 is called at least 1 time, depending whether function f5 is called 1 time or it doesn't call at all, we are in brown versus blue clusters. So this localizes the part of the code that most likely contribute to differential performance bugs. So this concludes the overview of this approach. Let's move on to the last part of this talk and illustrate experiments that show the scalability and usefulness. Perhaps scikit-learn is one of the most popular machine learning framework that supports various tasks such as classification, regression, and clustering. And logistic regression is one of the most important classifier inside scikit-learn, and it contains more than 3K lines of code in Python. So we start our process with fuzzing. We run the fuzzer for almost 2 hours, and we generate 185 functions, performance functions. So we consider two domains. On original program, we use a special computer to precisely characterize the response time. And then, as you can see, we characterize a performance function. Then we applied functional data clustering algorithms, and it returns 4 clusters, as you can see with different color in this plot. The fact that there are multiple clusters lead us to the next step to explain them based on program input features. So we apply decision tree on that space, and it provides us explanation. For example, it says that if we use different solvers, we will have different performance. So this is not unexpected. We expect that if we use different solver, we will have different performance. But the unexpected part is related to case where we have the same solver, but we ended up having 2 different performance, depending whether tolerance is 0 or bigger than 0. So we take that part further. On the instrumented version of the program, we generate the library's internal traces, and we have the corresponding cluster label using the clustering algorithms. Putting them together, again, we use decision tree to find out the discriminant model, and it pinpoints the condition inside optimized method. When we look at that part of the code, we are seeing the famous Newton iteration where there is a condition, and that condition compared the calculated tolerance against the given tolerance by user showing with told. We observe that if the given tolerance told is equal to 0, this loop doesn't terminate, even if the compute tolerance is 0. So it's going to unnecessary call to calculate gradient and loss. We reported this, and they confirmed and fixed this issue. And the basically fix is to convert strict inequality to less than or equal. We also noticed that the differences is related to 2 performance. None of them are the worst case one, in this case, blue and black one. So we need this approach to find out this performance. We also perform multiple other experiments, such as on bat generator. We found out that it's possible that the bat size is float number, and it causes huge performance behavior. It's also confirmed that has been since fixed by the developers. Another observation was for sample generator, where we reported 2 possible infinite loop iterations. The developers actually confirmed that issue as well, and they fixed this. But the interesting part of this fix is the rule of decision tree model that already tells the developers what they should do to prevent these performance bugs. We also perform on multiple other instances of libraries in machine learning. I also want to, and I encourage you to see the paper for the full result. And I want to also discuss a challenge we face. For example, in the case of regression trees, we observe that there is a quadratic behavior related to MAE criterion in the library as reported by the user, but we were not able to pinpoint exact location. And the reason was that they were related to external libraries. Those we need to bring the source of information from those libraries and enable us to do more precise analysis. So we left this as a future work. I also want to emphasize that this is not limited to machine learning libraries. Here, in the case of Apache FOP, the user reported that for similar input, it takes 7 times more for one than the other one. We do this analysis and find out that depending on the compression type on the input image or the size of the overflow part of these emails, we may have two different performances. So I also encourage you to see our ISSTA' 2018 about the fundamental of the clustering and how this approach is useful for Java web servers. In the case of SnapBuddy, that is also a Java web server, the users, Ashutosh and Anya, had different performances since they applied different photo filters on their public images. So we also basically explained, and this is also confirmed by developers. Finally, I also want to quickly mention that this approach is not limited to differential performance bugs. They can be useful to analyze side channels. For those of you interested in software security, I encourage you to see our ISSTA' 20 to see that how we adopt different parts to analyze this issue. With this, I would like to thank you for your attention. The source code and the benchmarks are available on the following GitHub that you can find. They are already evaluated, and I'm happy to take further questions at this time. Thank you.